taking different numerical here. A charge particle at t equals 0 a charge particle is at origin moving with velocity v naught as shown. So let me take this as A. So uniform electric field and uniform E bar and B bar are switched on. Find the instance of time at which it just touches the y-axis. Okay, different. I just changed the direction of magnetic fields. The uniform electric field, horizontal electric field, uniform electric field directed along x-axis is from x equal to 0 to a. It is confined. What is the magnetic field? For x greater than a, the magnetic field is present. I think in the books no further they are giving description. E is non-zero for x and B is non-zero for x greater than a. So because of electric field, the particle will accelerate. No? So when it arrives here, the same charge particle, when it arrives here, it will have velocity v. So what is the path? Path will be straight line because there's only electric field is there. Then after this, no. This is a positive charge particle. Better let me write here. Now what should happen to the charge particle? What should happen to the charge particle? What type of path? Again, it's a curved path, and since the magnetic field is greater than a, what is the radius of that? So definitely x is very much, so the magnetic field is action still almost for large distance. So it's going to describe semicircular path. Can you remember yesterday we discussed? So it's going to describe a semicircular path. Then it arrives here, not semicircular path. Okay, I think it appears now. So this is semicircular path. No. So after this, again, what will happen to charge particle? It will enter electric field with what speed? Enter magnetic field with the same speed. It will emerge out because work done by magnetic field is 0. Now it will encounter electrostatic force. It will undergo retardation. So due to retardation, so it will move along a straight line, and just it arrives at so what should happen to the particle now? Therefore, again it will encounter. So here it will have velocity u because there the electrostatic field is there for x less than a, right? So again it will go undergo retardation. Again will return back. No, I'm just putting x less than a. Even on this side also there will be electrostatic field. Let's assume that one. Or if you make it velocity 0 here, the problem will be much easier. Or if we can do one thing. Here it will come with a velocity v. I'll make it this one. So then what will happen? Due to electrostatic field, it will undergo retardation. When it arrives here, it will have velocity u. Because of electrostatic field, what happens? It will move further. Again, returns back, no? So definitely, shall I show the velocity here? First, u like this. Then again, or if you want, I'll show the path there. So it will be like this. Huh? So it should be like this. So show arrow like this. Yeah. Then again, it will enter magnetic field. So like that, what will happen to charge particle? It will be as long as that field is present. So I'm telling this, there are absolutely, I have seen around more than around 60 different types of numericals. So, but almost all are having same basic method, nothing big. So this you extend it. This will be the motion of charge particle. So again, every time, so it will be like this. So just if you want to show like this will be. Show only one arrow for the magnetic field. Here, whereas in the electric field, it will retrace path. So what is the time taken by it? Find the instance of time at which it just touches the y-axis. First, what happened? A t coordinate is here. So it will take some time to enter magnetic field. Again, the magnetic field will take some time. Again, it will trace out here. So add this time, and this time. Then again, what happened? This particular thing. So then it will be here. Again, this time will be same. This time and this time will be different. Time taken to move from here to here, and time taken this will be, this will be different. So if you just give the namings for this will be 1, 2, 3, 4, 5, 6, 7, 8. So time taken to move from 1 to 2 and 3 to 4 will be equal. Time taken 4 to 5 and 5 to 4, that will be equal. Time taken 2 to 3, it should be half of the time period of revolution. What is t to 3? T to 3 should be equal to half of the time period of 2 pi m by cube, you know, so pi m by cube. So at t equals 0, it will start from here. So calculate t12 from electrostatics. Then t23, you know it. T12 should be equal to t34. Calculate t45. How to calculate t45? Again, time taken for it to undergo retardation. So just work out. So there's a motion of charge particle. Like that, as long as the field and B bar is there, no, it will going to move that one. This is only ideal. Practically, there are a lot of such a symmetry not possible, because the boundary, the magnetic field exactly suddenly will not become zero. On paper, just to attract students, we are just bringing all these numericals here. In the lab, nobody is this one. So a lot of problems will come. B bar is non-zero, suddenly becoming zero. I think not possible, no? B bar here, non-zero, suddenly becoming zero, not possible. It's very difficult to construct all such things, and also this on paper, all these such numericals will be available. Okay, now take this. Some way gravitational force also will bring into picture. Read the question. Consider a region containing gravitational field G and the magnetic field B as described below.